Hi everyone, my name is Liang. I come from City University of Hong Kong. I'm going to talk about a fine-grained cache file management framework. It aims to improve mobile performance and lifetime by handling cache files separately. First, let's look at the overview of this talk. The target problem is that readbacks of cache files negatively impact mobile performance and lifetime, but some of them are not necessary, because we found that most cache files stored in flash storage will not be read again before they are deleted. We further analyzed cache files at application level, file level, and read pattern level, and found they are different. To improve the performance and lifetime of mobile devices, we propose FCFM, a fine-grained cache file management framework to manage cache files according to their features. FCFM mainly categorizes cache files to three classes: burn after reading, BAR. In this class, the files can be discarded after usage. In transient class, files should be stored in memory. For long-living class, cache files will be stored in flash storage. A preliminary evaluation showed that the proposed solution can much reduce the rate operations of cache files. Okay, we know most mobile applications need to download cache files from networks, such as news and videos. However, the speed of network is slow. Requesting data from memory is the fastest. Even reading data from flash storage is much faster than from network. Thus, to improve the data retrieval performance, mobile system temporarily stores the cache files in the local storage. But we want to know, how do these cache files affect mobile devices? It is a consensus that cache files negatively affect performance. When your PC or mobile device is getting slow, if you look for a solution on websites, there's always an advice for improving performance by deleting cache files. The performance degradation is mainly caused by error contention that induced by cache file writebacks. Moreover, cache file writebacks will trigger garbage collection of flash storage and thus also reduce the lifetime. Then, what is the proportion of cache file writebacks in total I/O? This figure shows the percentage of cache files writes in the total I/O for 10 commonly used applications. The blue histogram represents write amount ratio. The orange one is write count ratio. The key takeaway here is that for some applications, the cache file writes accounts for a large percentage of the total writes. Thus, we need to reduce their negative impact. To reduce the negative impact of cache files, we analyze cache files on a real mobile device, Huawei P9. We collected data for 2 hours with 10 commonly used applications. Based on this data, we can analyze cache files under one of common scenarios for each application. First, we analyze cache file at the application level. This figure shows read and write amount of cache files in flash storage. The blue history is read, and the orange one is write. Based on this data, you can see that cache file access of different types of applications vary greatly in terms of total data amount. Moreover, on average, the write amount of cache files is 100 times more than the read amount. That means most of cache files do not need to be written back to flash storage. So we further analyze cache files at file level to find what kind of cache files do not need to be written back. This is a read amount. Y-axis is read amount ratio. We ordered the cache files according to their read amount. and the x-axis is the index of ordered files. Different color is different applications. And this is the write amount. We can see that compared to write, most of read amounts of applications are concentrated on few cache files. Thus, if only storing this small set of cache files may improve user experience. We further analyze the cache files from other dimensions to figure out what kind of files should be stored. We analyze the read amount of cache files according to their lifetime, size, and file number. X-axis is the lifetime of cache files. Lifetime more than 2 hours we call long lifetime. The histogram represents the number of files with the same lifetime. The numbers above the histograms are the read amount of these cache files. The line chart represents the total size of files with the same lifetime. The results show that for most applications, most of reads are conducted on the long lifetime cache files. Moreover, the total size of these files is more than 50% of total size of cache files. That means if discarding the short lifetime cache files may halve the writes on flash storage with small performance penalty. Finally, we analyze cache files at read pattern level. This figure shows the read pattern of the 10 most read cache files of each application. Each frame represents an application. X-axis is the time. The selected cache files in each application are displayed by 10 colors. The dot is read. Since many read operations upon a single file could happen in a short period of time, we merge the number of reads of a file in every 80 seconds. Thus, a larger circle represents more reads in this period. The results show that from the temporal perspective, the cache file basically shows two types of read patterns. The file with concentrated reads in a short time period, and the files are contiguously read across the application execution time. All these observations shows that not all cache files are equal at application level, file level, and read pattern level. That means we need to manage them differently. Based on the observations, we present a fine-grained cache file management framework, FCFM, to improve the performance and lifetime of mobile devices by exploiting the features of cache files. FCFM categorizes cache files to 3 classes and maintains them in main memory and flash storage hybrid architecture. The cache files in burn after reading class will be discarded after usage. The cache file with a large write amount but a tiny read amount could be stored in this class. The cache file in transient class will be stored in memory file system. The cache files with a large write and read amount as well as a short active period could be stored in this class. The cache files in long living class will be stored in flash storage. The cache file with a large read amount and a long active period could be stored in this class. The key idea of proposed FCFM is to treat different cache files separately. We use video cache file of YouTube as an example to evaluate FCFM framework. In default file system, all video cache files are stored in flash storage. There's another choice is to store all video cache files in memory to reduce read-back operation. Compared to the baseline, we can see that the write amount is reduced, but the write number is increased. This is because some memory space is used to store the video cache files, and thus other files will be evicted from memory to produce write operations. According to FCFM, video cache files belong to BAR class. Thus, these files are discarded after usage. The results show that compared to the above two methods, FCFM can much reduce the write amount and write number. And thus, it can improve performance and lifetime of mobile devices. Now, let's look at the penalty of FCFM. Since 2% video cache data will be read, thus they need to be downloaded again. The penalty includes latency, energy, and money. Based on the above analysis, we find that FCFM can improve performance and lifetime of mobile devices with a small penalty. But there is still some challenge for implementing FCFM. First, how to systematically categorize cache files. We know that when a cache file is downloaded, the system does not know its exact features. Second, how much RAM should be used for a memory file system? There is a trade-off. If it is too small, there is not enough space to take advantage of FCFM. If it is too large, it could negatively impact other files. Third, we need a file-based eviction scheme. Page-based eviction scheme such as LRU is not suitable for cache file eviction because when a page of a file is evicted and discarded, the whole file will be invalid. Now, let's conclude this work. We found that unnecessary cache file writes negatively impact mobile performance and lifetime. We further found cache files are different at application level, file level, and read pattern level. Thus, to improve performance and lifetime, we proposed FCFM, a fine-grained cache file management framework to manage cache files according to their features. FCFM mainly categorizes cache files to three classes. Burn after reading. In this class, the file can be discarded after usage. In transient class, files should be stored in memory. For long-living class, cache files will be stored in flash storage. A preliminary evaluation showed that the proposed solution can much reduce write operations of cache files, and thus improve performance and lifetime of mobile devices. Okay, that's all. If you are interested in our work, please check our paper by scanning the QR code. If you have any questions, please feel free to contact us. Thank you for listening.